bending stresses. So bending stresses, according to the engineering syllabus, involves analysing beams that are under point loads, and you need to work out the shear stress and bending moments. You also need to work out the shear force and bending moment diagrams, and you have to understand the concept of the neutral axis, which we covered in a previous video, and outer fibre stress, and do some calculations involving ultimate bending stress. You also need to know the concepts underlying the uniformly distributed loads, and with this you can evaluate the importance of these diagrams and understanding the materials of properties, the properties of materials, and you can also draw these diagrams yourself and do basic calculations. Alright, so what is outer fibre stress and what is the neutral axis? We covered this in the last video, but just briefly, when a beam is loaded, it tends to bend. As you can see in this diagram down the bottom, if you have a simply supported beam with a load acting vertically downwards, it'll force the beam into compression in the top layer. So this side will tend to be forced inwards, so it's being forced like this as it bends, whereas the bottom is being forced outwards. And because these two forces are opposing, so this one's in compression, and this one's in tension. So somewhere along the middle, there has to be a point where it is neither in compression or tension, and that's known as the neutral axis. So when you're loading a beam and it bends, you can have a positive bend, and that essentially just looks like a smiley face, or a negative bend where it's bent upwards. You can also think of this as a parabola. This one is concave up, this one is concave down. So beams are strongest when the largest amount of the beam's mass is placed at the greatest distance from the neutral axis, and this will come into play when we're doing calculations involving ultimate bending stress. So bending stresses. We have our simply supported beam, as stated in the syllabus, and we have to analyse it in regards to vertically loaded, some vertical loads. So first what we have to do is find the reaction forces, and the way that we can do this in a beam that's in equilibrium, such as this, is we can use the sum of moments about a point as equal to 0, the sum of forces in the y are going to be equal to 0, and the sum of forces in the x are all going to be equal to 0. Here, we've only got forces acting in the y direction, so we can ignore the sum of forces acting in the x. We see that this is a roller support, so we know automatically that it's only going to have a reaction going vertically upwards. And this is a fixed support, so it could have a reaction going to the sides and one going up. But we know that here, the loads are only acting vertically downwards, so this is simply going to have no x force to combat. It's just going to go straight up. So let's take moments about the point B, and we'll work out the reaction at A, because we're getting rid of this unknown, because it's got a perpendicular distance to B of 0. So sum of moments about point B has to equal 0, and let's take this one. This one's going to turn it that way, about point B. So we'll go this direction is positive. So we have 40 kilonewtons times 3 plus 30, because it's turning that way. 30 times 9, it's got a distance of 9, minus the reaction at A, it's going to turn it the opposite way, so it's a minus, and it's got a distance of 12. So minus RA times 12 has to equal to 0. So solving that, we get that RA must equal 32.5 kilonewtons vertically upwards. So 32.5 kilonewtons. And then we can use our sum of forces in the y to work out the reaction at support B. Let's take up as the positive direction. So we have 32.5 minus 30 minus 40 plus reaction B, y equals 0. So reaction B, y, is going to be equal to 37.5 kilonewtons, and that's going to be vertically upwards, and we know that there's no reaction force in the x direction, so the reaction at B must be 37.5 kilonewtons. Excellent. Now that we have those reaction forces worked out, we can go on to calculating the shear force diagram. So as you can see, we've retained the same beam, but now we're wanting to work out, well, what's the shear force acting upon this beam? Remembering that shear force is a sliding force. So as you can see over here, if you have two things, and one's being dragged this way, the other is being dragged this way, a shear force, so that's a sliding force, will be induced along this plane here. So when a beam tends to bend, if you have a bending beam, it's going to induce a shear force within that beam, as there's going to be two forces opposing. We know that this is in compression and this is in tension, so we've got those two opposing forces. So we've got that shear force acting along the neutral axis. So we want to work out what the magnitude of the shear force is going to be at different points along the beam. This will help us to work out where the forces essentially are greatest, and that'll help us in our calculation of ultimate bending stress. So the way we do this is quite simply, we take our shear force diagram. So it's just a simply loaded graph. So this axis is the force, and this axis is the distance, and distance is going to be in meters. Force we're going to have in kilonewtons here, just for simplicity. As you can see here, it's shear force in kilonewtons. So basically all you're doing is you're taking up, so any forces acting upwards are positive, and you're drawing them on this axis. So this axis lines up with the diagram above, so you're just dragging them straight down. So we see we've got this force, 32.5 kilonewtons acting straight up, and that lines up right with the y-axis. So we're going to draw, let's go up here, 32.5, and we'll place a point there. Alright, we're going to go across to the next point, so that's going to line up with the 30 kilonewtons. And if we drag that down, this should give us a distance of 3 meters along there. You don't need to label that, but it might be helpful to do so. And we're going to extend the point to there. So our 32.5 is acting in that way. And then we're going to drag it down, because the 30 kilonewtons is acting downwards. So we're going to drag it down, and 32.5 minus 30 gives us 2.5. So we're going to have another point there. Now we're going to do the same thing. We're going to see where the next force is acting. So that's going to be a 40 kilonewtons. If we drag it down, we get this as a distance of 6 meters. And we can extend our point at 2.5 kilonewtons out to here. So if we take that point out there, then we can connect up this line, and then we go down an additional 40. So if we go down 40 kilonewtons again, that's going to take us to negative 37.5. So we've gone below the x-axis, so down to negative 37.5. And then we're going to drag that across. The next one is the reaction at B, 37.5. We'll drag it across just in that manner. And hey, wow, the next force is acting upwards, 37.5 kilonewtons. And that's going to take us right back up to the x-axis. So an important thing to note with these diagrams is if the beam is in equilibrium, you should always start and end on the x-axis. So here we're at the x-axis, here we're at the x-axis. And I also want to make a point of where it crosses the x-axis. That's going to be important for our calculations for the bending moment diagram. So what we can do with this is see, well, we know that there are different forces acting on this beam, and this is a way of representing that. From there, we want to work out the bending moment. So a moment is force times distance. And remember how before we described this as the distance axis, and we had distances along here. All we're going to do is times the height of each of these boxes by the distance, and we essentially want to find the area of the shape created between the line and the x-axis. So this first one is going to be 32.5 times 3 meters, which gives us 97.5, and that'll be in kilonewton meters because we're timesing distance by a force. And then for this one, we have a height of 2.5 and a distance of 6. So we times 2.5 by 6, we get 15. So 15 kilonewton meters. And if we times 37.5, which is this distance, by 3 meters, then we get 112.5 kilonewton meters. Alright, so we've got that labelled. Now, these are essentially the moment forces acting along these planes. So what we can do with those is then draw up our bending moment diagram. So this represents the bending moment. So remember, a bending moment is when it forces it to turn. So in a loaded beam, we know that there is some turning action happening because so when it's being pushed downwards, there's a force, and that's why this is in compression. It's being dragged in that way. So that's a bending moment. And this one is being forced outwards, so there's another bending moment kind of acting like that. So drawing this is a very similar principle on the graph to our shear force. So essentially what we're doing is we're taking the distance calculated, and we're using the values calculated here as the distances that will go up. But here we're always going to start at 0. So we start at 0 and then we go up to our first distance. And we want to plot that in line with the edge of this box, essentially. So we're going to go up, because it's above the x-axis, 97.5 kilonewton meters. So kilonewton meters, we go across to here, and this is 97.5. Alright, and then we can extend a line from 0 up to there. The next point we have, so we've got 15. So we've got 15. We're going to have that above the x-axis. So that means our graph needs to extend up an additional 15. And it's going to go until where this point is. So drag that across. So let's take this dot over here up 15, which will give us 112.5, and we can connect those up. There we go. And then we have this box here, which is below the x-axis, which means that it's going to go downwards, and it's 112.5 as well. So that's going to land us right back onto the x-axis. Perfect, so that's an important thing to note. We should always start and end on the x-axis when it is in equilibrium for the bending moment diagram, as well as the shear force diagram. Now remember how there was a point here on our shear force diagram where it crossed the x-axis. As we can see, this lines up with the highest point in our bending moment diagram. And this highest point is called the maximum bending moment. And that's going to be very important for when we get into our calculations of ultimate bending stress. So as you can see, when they're lined up, you have both these diagrams just like that. And the maximum bending moment there, that's the maximum bending moment the beam can withstand. Well, it's the maximum bending moment that's applied at the beam. It's 112.5 kilonewton meters. And as you can see, overall, the graphs of all three things are going to, so both graphs are going to line up with your original loaded beam. So you should have these points lining up roughly with the loads applied in that first loaded beam diagram. And that's an easy way to draw it in an exam. Just take a ruler, you can draw through the question and you just line it up in that way. So, finding your ultimate bending stress, it's a calculation which is on the formula sheet, and the formula for it is ultimate bending stress. So, ultimate bending stress is equal to my on I. So what does that mean? Well, m, we noted before, that's your maximum bending moment. And we find that from the bending moment diagram, as you can see in this image. So it's the point of greatest displacement on the bending moment diagram. And it doesn't always have to be above the x-axis. In some cases, you might get a graph that looks like this, and you might have your maximum bending moment here. That's all right. You take the exact value of it. So if it's a negative value, say this was negative 112.5, the maximum bending moment would be 112.5 kilonewton meters. Okay, what is y? Y is the distance from the top of the cross section to the neutral axis. So as you can see in these diagrams, if you were to take a cross section of a beam, so you have a square beam, you find the neutral axis, usually they'll give it to you where it is, and it's the distance from the top of the beam to the neutral axis, not the bottom of the beam to the top, not the bottom of the beam to the neutral axis, because that'll be a different distance. And as you can see, it's the same for an I-beam. You take the distance from the top to the neutral axis, and even for a rounded beam, it's the distance from the top to the neutral axis, and that gives you your y value. And you want to make sure that y is always going to be in meters. Often these measurements will be given to you in millimeters. It's important to convert that. So I is the second moment of area, and basically that's a constant that is representative of the beam's stiffness. So that calculation will always be given to you. There is a way to calculate I, but we do not need to cover that in the engineering studies course. And often this will be given to you in meters to the fourth. So the units for that is meters to the fourth. Often they'll give it to you in millimeters to the fourth. So it's important to convert that into meters. And in order to do that, you go millimeters. Well, millimeters to meters is times 10 to the negative 3. And that whole thing to the power of 4. We will give you the right units for these calculations. So a strengthening effect occurs in I-beams because there's a greater distance from the neutral axis, from the majority of mass to the neutral axis. So as you can see in our formula, the greater the value y is, the greater the overall stress value will be, because this upper number is going to be larger. So when it's divided by the same constant, you'll end up with a greater result. So let's do a sample calculation, taking all of this into effect. So if we go back to our diagram here, and they asked you to find the ultimate tensile, the ultimate bending stress in our beam, and they've told you that I equals to 50 times 10 to the 4 millimeters to the fourth. So our calculation would go like this. So ultimate bending stress is equal to my on I. You can find that on your formula sheet. We go our m value, which is here, so 112.5, and it's kilonewtons. We need to make sure that this goes into basic units, so into newtons. So times 10 to the power of 3. And then y, usually they'll give you y. Let's say our beam looks like this, and we've got this here. And they tell you that the overall distance is 100, and that this distance is 60. Well, we want to take the difference of the bottom from the top. So we'll work out that this top distance, our y value, is going to be 40. and that's going to be in millimetres if they don't give you units. You can assume it's in millimetres. So we're going to go times 40 times 10 to the negative 3, which will get us into metres, over our I value. So we want to convert this into metres to the fourth. So 50 times 10 4 times 10 to the negative 3 4. And that'll give you your value. You pop that in the calculator. Oh, and it's also important to note that your ultimate tensile, ultimate bending stress calculation will end up in pascals. And it's usually a big calculation, so often it'll be in megapascals. UDLs, so this is part of the syllabus as well. It is uniformly distributed loads, which we covered in a previous video as well. How these apply to your bending moment diagram is basically you get a shear force. It's going to go straight down just like this. And then your bending moment is going to look like a curve. So you don't actually have to do calculations involving this, but you have to recognize these facts, that in a bending moment diagram, it's going to end up as a curve with the maximum bending moment at the peak of that curve, and the shear force is going to be a line going diagonally through some sort of point. That'll often come up in multiple choice. Cantilever beams. This hasn't come up very frequently, but technically they could assess you on it. So cantilevers are a little bit different in that they will not start and end at the neutral. So they will still start and end at the neutral axis. So we know that this will have a reaction of 7 kilonewtons up. This is 7 kilonewtons down. So we have a beam that looks like that. And that'll give us a bending moment diagram. Basically just goes down and then a line like that across there. And your maximum bending moment, of course, will be where the only support is, because you're not really going to have a moment force acting at any point other than where it's attached to the wall. So that covers the shear force and bending moment diagrams. And these are very handy for civil engineering, as when you're selecting a material to use for your bridge or something like that, if you understand the characteristics of the material you're using and what it can withstand, then you're able to put it in appropriate situations where it's not going to be overloaded and it's not going to experience stress or moments forces that it cannot withstand. That'll help to improve the safety of users and make sure that they're not using unnecessarily expensive materials or something that isn't going to withstand too much force.